Hey, and welcome to Topic Partition, a new podcast about Apache Kafka. To kick off this very first episode, I have two special guests joining me today. I have Ivan and Greg from Ivan. These are two senior engineers, part of the authors of the new KIP-1150 that introduces diskless topics to Apache Kafka. A diskless topic is a topic which writes its data directly to S3 without replicating between brokers. It doesn't have leaders. Any broker can lead it. And as the name implies, it doesn't actually use any sort of disks. Turns out that when you remove the state from brokers, you make them stateless, you can remove a lot of the operational problems that we face today in managing Kafka clusters. And by eliminating the interzone networking between brokers, you get a Kafka that's literally 8 to 10 times cheaper. This was a very long podcast. We went through a lot of topics. I have 3 full lists of questions that I wanted to ask the authors, and we probably got to 75% of everything. It's a very technical deep dive. This is not one of those podcasts where we talk about like, oh, what got you into Kafka? What does Ivan do? Yada, yada. No, we just dove straight into the KIP and all the technical details around it. We covered things like the latency trade-off. We covered the batch coordinator. We actually talked a lot about the batch coordinator. We talked about different implementations of the batch coordinator. We talked about the way that clients bootstrap in this new model. We talked about S3 Express. We talked about how production ready this system is. Turns out Ivan actually has it running in production right now. We talked about alternative KIPs that came out following this KIP. We talked about table formats even. We talked about Parquet and Iceberg. We talked about bottlenecks in the system and how those could be alleviated to partitioning of the coordinator, for example. It is very technical, honestly. It's something I recommend for engineers. If you're not very technical, maybe you won't get too much out of this podcast. But even then, we try to make the podcast easy to get into. So you don't really have to be a Kafka expert, or you don't even have to have read the KIP to understand any of this. We try to explain everything from the ground up in very simple terms. It's just 2 hours and 30 minutes straight of technical talk. I recommend you just grab a coffee or 3 or 4, strap in and just listen to the whole thing. You'll be much smarter for having done it. All right, welcome to the show. Thank you so much for coming on, Greg. I have with me Greg and Ivan. I have so much to ask you today. I have like three A4 lists of stuff I want to hit on, so it might be a long podcast. But before that, please, let's do a quick intro. Can you say a few words about yourself?
Of course, Ivan, you want to go first?
Yeah, well, of course. So, hello everyone. I am Ivan Yurchenko. I work at Ivan in the streaming domain, mostly focusing on Kafka. And I worked with Kafka maybe for 8 years or more. First as a user, then I joined Ivan to develop some open source stuff around Kafka, and then I went full in and been there since then. Yeah, Greg, please. Now you.
So my name's Greg Harris. I am a full-time contributor to Apache Kafka, and I have been for coming up on 3 years now. I also work for Ivan, and I'm very fortunate to be able to work on Kafka. And before Ivan, I worked for Confluent for 3 years. So I think I've been in the Kafka space as a Kafka developer for about 6 years now. I'm currently a Apache Kafka PMC, and I've done a couple of talks about Kafka and Mirror Maker things in the past. So thank you very much.
Nice, yeah. Yeah, we were colleagues in Confluent, but we never really worked together. We were in separate teams.
2 ships in the night.
Yeah, Ivan, we were missing you only. All right, so I want to talk about Diskless today, right? So you came out with this bombshell KIP out of nowhere. If I can just sort of lay the ground for all the listeners. We had Kafka shipped in 2011 or something. It was this distributed system made for data centers, and it was made to scale on commodity hardware, so scale horizontally by just adding new brokers. And commodity hardware back then meant hard drives, so just cheap hard drives. Nowadays, SSDs are cheap too, but back then it was hard drives. And basically the whole system was sort of optimized around that. Now, then we had the cloud, and people started deploying Kafka on the cloud. We started changing some stuff. Confluent, in particular, started changing some stuff around Kafka to make it more cloud native, etc. And then 2023, WarpStream launched. And WarpStream had this diskless sort of design where it rolled directly to S3. And then it seems like everyone else followed. Confluent came up with a competitor product, BuffStream launched, etc. And then, I don't know, what was it, like a year later, Confluent bought WarpStream for like more than 200 million after just a year and something of the startup working. So there has been this diskless craze in Kafka. And then you come up with a KIP saying that you're going to introduce it in Apache Kafka in the open source. So I guess the question I want to start with is like, what's wrong with disks? Like, why did all of this happen? Can you sort of walk me through that?
Yeah. Well, disks are okay, but cloud cloud disks are a bit more expensive than some people expect. But apart from disk, we have network traffic, because usually you want to replicate your data in Kafka between brokers. And as you deploy Kafka in clouds, you want to deploy brokers in different availability zones. And on most Kafka, on most cloud providers, network traffic between availability zones is not free. It actually costs quite a lot if you run Kafka at scale. So, and this diskless design, diskless idea, eliminating disk was not the primary motivator. The primary motivator was to eliminate replication and replication network traffic. Yeah, so Greg, maybe you want to add something to this.
Yeah, I would also say that definitely the change comes from the clouds that are ever present today in the software ecosystem, and the new pricing models that everybody has. I mean, Kafka makes sense if you're buying a hard drive and you're running it for 2, 4, 6, 10 years, because the hardware will amortize very well. But when you're looking at an ongoing monthly cost for storage, an ongoing monthly cost for data transfer, the actual usage tends to matter a lot more. And so these sort of inefficient usage patterns of the classic Kafka style, they are just selected against by the pricing models. And part of making something cloud native is not only making it more agile and more deployable in the cloud, but also making it cost effective.
Got it. So, but we have replication. We have replication for a reason, right? We have it for availability purposes. So we have the data on a few nodes. If one dies, another can take over immediately. And we also have it for durability. So if you lose one node's disks, you don't lose your data. There's 2 other copies. So how do you solve against that if you eliminate replication?
Well, I think the big element here is that you're relying on the sort of underlying replication outside of a disk storage system, and you sort of adopt the durability properties of whatever system you're putting data into. So in a classic topic environment where you have to deal with the failure of an individual disk, you have to do that replication yourself. But we now have abstractions where we can give one block of data and the replication is handled sort of behind the scenes. And that can enable very strong cost optimizations through the use of erasure codes and parity checks and all of that sort of stuff. And it's the reason why S3 is so cost effective in general.
Right. So when you say these abstractions, you're just talking about object storage. So S3 and the equivalents in other clouds.
Yes. So a lot of this is designed to be vendor neutral. So object storage as a general abstraction has become a very standard offering in like all of the clouds, basically. The specific implementations like are less important, and the specific cloud providers are less important, but the abstraction is what matters.
Right, yeah. I would assume that S3 is probably the most used service in AWS, or really close to EC2.
Yeah, I don't know the numbers, but I could believe it.
Yeah. Okay. Can you walk me through then the architecture? Like, how does it work if you're just leveraging S3, like at a high level?
Well, I maybe we can start and then pass the ball to Greg. So, let's assume we have brokers and we have producers that send produce request to the broker. So we can go like naive way and just take the produce request and upload whatever data we have in the request to the object storage. So this will probably work, but it will be very expensive, like astronomically expensive, because that's it, due to the interesting cost model of object storages. So they are cheaper than disks, but in contrast to disk, you pay for requests. So you pay for get requests, for put requests. Put requests are usually about 10 times more expensive than get requests. So writing every couple of kilobytes to the object storage is a costly idea. So we can amortize this cost by just accumulating enough data to the point where we can tolerate the cost. Let's say, like, for example, in the design that we propose, we use time-based buffer, 250 milliseconds by default, or like size-based, whatever comes first. So once you accumulate enough data to satisfy one of these conditions, then you upload this object to the remote storage. And the beauty of the idea is that you can do this in parallel on different brokers without any coordination. So they just need a mechanism to generate unique names for files, for objects, and upload them independently. Then comes committing magic. So maybe you, Greg, want to tell about how this orders.
Yeah. So once these objects are uploaded containing lots of batches of data from different producers, they really don't have any global ordering or any relation to the other objects in the cluster. They only have sort of an order relative to one another inside of a single object. So if you produced one batch and then a second batch, they would have an order saying that one came first. But if you produced one batch on one machine and a batch on a different machine, they wouldn't necessarily have any order. It couldn't determine which one is first. So the batch coordinator committing essentially is what gives us that order. It's a node that is responsible for deciding the total order of all of the records that are in a topic. This is a job that was previously just the leader's job. So when you would produce data to a broker that was the leader, it would assign offsets because it was sort of the authoritative source. And now that people or the brokers are able to upload data without being an authoritative source on a single topic, that responsibility has been moved to a batch coordinator. And this is a lightweight operation overall. You don't actually have to handle any of the data in order to assign offsets to it. You just need to know sort of some identifying information about the batch, where it's located in the object, what topic partition it's for, which producer produced it, etc. All of the sort of header information. And from just the header information, the broker or the batch coordinator is able to determine whether the batch is a duplicate, where it should be located in which partition, and it can commit that finally and store it so that it can be queried later. And once you query the data, then the broker can pick it back up. So Ivan, you want to cover the fetch side?
Yeah, well, just
Boyd, I have more questions here.
Okay.
Yeah.
So that was a lot actually. So first you say that like brokers take in data and then they buffer it for 250 milliseconds by default, and you said something along batches and objects, but you know Kafka has like when people talk about Kafka they talk about like records and partitions. So where is the partition in this object? Can you sort of clear that up?
Yeah. So well, batch. When we say batch, we speak about record batches. So, and batches are fundamental to the Kafka protocol. So Kafka stores data in batches on disk. Kafka transfers batches over network. So it's batch everywhere. Because, well, single partition, like addressing single partition might be costly. Oh, sorry, addressing single record might be costly, despite they have offsets. But they also have meta information about compression and stuff like this. So, and Kafka just tend to group records in batches to like reduce the metadata overhead.
So like a batch is like So a batch is like 10, 20 messages in one bundle.
Yeah.
That's how
So
we can think about it.
this actually depends on the producer configuration. You can, like, if you configure linger MS and max batch size, those are settings like this. So, but you can tune from one single record to multi record megabyte size batches. So yeah, and then partitions, you said, right? So partitions don't go anywhere. We keep them. Basically we try to keep that just high level theme that we try to keep as much compatibility with existing Kafka protocols, clients, and high level concepts like partitions as possible. So probably we can make topics like Diskless topics partitionless. But if you really want partitionless topics, just create a single partition topic. So
Got it. So you're respecting still the APIs and everything remains the same, and
yep.
producers still write, records in certain partitions. Well, then, I mean, the next question that comes to me then is like, how does keying work? So some producers use keys to partition to a particular node. How does that?
I mean, that also stays the same. So if you have a partitioner that works for your workflow and you find that it serves the scale of your consumers very well, it can all be transported directly into the Inkless context. You can also have keyless topics where you don't key the data and you just let the partition assigner decide, and that will also work with Inkless. Many of the fundamentals of the classic topics are still around. It's why this is a new type of topic, not a completely new thing. And it's why we're able to offer very deep compatibility with a lot of existing applications.
Got it. So if I understand correctly, then data comes into this broker, it batches it into this one object, which has data, or it has record batches, many records of multiple partitions, and then that gets uploaded to S3. And because if you're using, let's say, a partitioner, it will always give you, that producer will always produce for a particular partition, which really just tells you, I want that to go to the same broker, because I want, if a producer sends message 1 at timestamp 1 and sends message 2 at timestamp 2, you want 2 to come after 1, right? You don't have that ordering within a single producer client.
Yeah. This actually brings us to this topic that we already touched lightly, that in Diskless topics, we don't really need leaders for partitions. So every broker in the cluster could write and could read to and from the partition. So basically the sequencer, the batch coordinator, is responsible for ensuring the order, but the rest is happening independently. And we will touch this topic again later when we will speak about costs and inter-AZ traffic and how we remove it.
Okay. And then, so I guess we're talking about the coordinator next. So brokers have these batches, they upload it to S3. How do they, if everyone is a leader, how do they know what the offset for a particular, what determines the ordering?
I mean, that's the funny thing is they don't. At the time that a producer produces to a broker, that broker does not know what the last offset in the topic is. So it really is not empowered to assign offsets. The component that does know the end offset of every partition in the cluster is the batch coordinator. So the batch coordinator is able to actually do sort of like an atomic append at the end of the topic and increment the end offset and do it just like the leader does. It just sort of keeps state around in order to remember where the topic is and can atomically append to it. But it means that by the time the data is uploaded, it really does not have offsets in it. It's sort of like offsetless, or also we've been using the term like a write ahead object or a write ahead format.
Yep. Got it. So it writes the object, asks for the offset, and then when it has the offset, when the offset is determined, what happens then?
Yeah. So now it needs to a broker tells a batch coordinator that, hey, I have this object full of data, and here is a list of batches for all their, like, what partitions they belong to, and the timestamps and various meta information, about 100 bytes of meta information per batch. And then the coordinator, it goes to this to its internal database or data structure. Depends how on the implementation, how it stores everything. So it checks, okay, like this is for example, like topic ABC, partition 0. The last offset, currently the high water mark is 223. And then it takes the first batch that it belongs to, like first new batch that belongs to this partition, and assigns this 223 to it. And then it does this for all batches, and this collects responses for the broker, because broker must respond to the producer with assigned batches. Assigned offsets. So this goes like full chain back to broker and then to the producer. So from the producer point of view, nothing changes. So the protocol is the same. It gets the same expected values, like high watermark, log beginning offset, and stuff like this.
Got it. So let me run again. You can tell me if I'm correct. So a broker receives produce requests which have data. That broker buffers it. It's worth saying every produce request has data for multiple partitions, multiple topics. And at the end of the day, after 250 milliseconds, that broker uploads an object to S3, which has the data of all the partitions it got data for in the last 250 milliseconds. Then sends a request to a batch coordinator, which assigns an offset for every partition in that sort of batch, which returns the offset, and then the broker starts responding to all of those produce requests. Is that correct?
Yes, that is correct.
Nice. Okay, then I want to ask more about the coordinator then, because the KIP says it's going to be pluggable, and you have like 4 different bullet points of how you can implement it with a Kafka topic, with a standalone database, with a k-raft quorum, even by object storage. I want to dive into all of those, but you also like tell me like how do you think what is the best implementation, or does it matter? Like how do you want to even start describing that?
I think in the ideal case, it would be nice to rely only on object storage. So if we could say that it was truly diskless, all of the data only gets committed when it goes through object storage. It would make it so that you had like fewer dependencies on a cluster, because you would be able to store both the objects containing the data and sort of manifests of the metadata that store all of the information. Now, that requires a little bit more design work, in that you need to have a protocol where you can commit from multiple machines at once and have the object storage sort of mediate as to who finally does do the append. So there are some technical challenges in front of that, and ultimately, well, I was going to say that we don't have an implementation of that yet designed, for those reasons. Like we haven't found that it's really been viable, but it does seem to be sort of the most pure design overall, if it can be put together.
Yeah, I believe it can be put together because, well, S3 and other object storages have compare and set operation, which is like conditional write. So, and on conditional write with enough layers of abstraction, you could implement any transactional madness you want. So the question is like how cost effective and like latency effective it would be. So that's an open question that requires investigation.
Yeah, I want to talk about latency later, but also about the coordinator now. Is there only one coordinator in a cluster?
So it depends on like how we define it. So, for example, when we implemented the Postgres-based coordinator, so you like the class that represents this coordinator, it's instantiated, created in every broker. So, but if we look like not from like formal point of view, but from like real where the coordination is happening. It's happening inside Postgres. So it means in this case, it's like one node that does coordination. Others are just like interface to this node. If we take a hypothetical non-existent etcd-backed coordinator, you just have a cluster of etcd machines with a leader that does the writes and does all the like transactions and stuff like this. So ultimately there will be, well, I wouldn't be like super categorical, but probably there always be one leader in this coordination constellation, be it one machine or multiple machines.
Yeah.
Interesting. So, sorry, go on.
So I was going to say that it is very important that there is one leader, because you need to be able that leader needs to be able to give an authoritative answer on where is the end of the topic, and you sort of can't have multiple nodes responsible for that without running into sort of cap theorem problems. So it's just sort of like a classic distributed systems problem, and the leader approach is what Kafka's done so far, and so it's very natural to sort of expect it again. Now, what Ivan was mentioning about multiple leaders is that you can theoretically have multiple batch coordinators serving traffic for a cluster, as long as no batch coordinator is the leader for, no two batch coordinators are the leaders for a single partition. So essentially, you can't have a split brain scenario where a single user partition has to store data in multiple different batch coordinators. It needs to be a single unambiguous batch coordinator, just like how the Kafka metadata has to elect an unambiguous leader for a classic topic partition.
Got it. So basically, you're telling me it's not actually serverless. It's not actually leaderless. The leaders are somewhere else.
Yes,
And,
the leader has now moved from the edge of the cluster, which is accepting data, further inward, where it's only handling metadata. But there still is a leader. It just is not in your zone.
Yes,
Right,
that's
that's
a very popular pattern in distributed systems. Well, it might be like in a narrowly scoped to like separation of storage I/O and sequencing or ordering, or it can be like a bit broader, where you separate like I/O of real huge volumes of data from metadata, the tiny, relatively tiny volume that can be handled more efficiently, like outside of your like edge nodes.
right. So that's the key thing we're touching on here: the separation of data from metadata. And because metadata is smaller, you can scale it up a lot more. So probably, a reason why a Kafka leader, why you just can't have one Kafka leader in the whole cluster, in the classic mode, is because the disk won't allow you. You can't scale that much. The CPU won't allow you, etc. You have to write too much data to disk. But now that you're only handling metadata, you're telling me that's much more scalable. So I want to touch on the Postgres one a little bit more. So to give some context to listeners, you just released Inkless. Now that was released yesterday. We're recording this on a Friday, and Inkless seems to be your fork of KIP-1150. Your implementation of 1150, intended as a short-term fork that you eventually just want to merge into the mainline. Let's speak a little bit about that, and then I can ask about the Postgres coordinator there that I saw. Tell me more about it.
Maybe you.
Yeah, sure. So yes, Inkless is our short-term fork. When we were sort of pursuing this project and considering writing a KIP and figuring out how we wanted to tackle the project, we sort of needed to prove to ourselves that such a thing was possible within Apache Kafka. We were familiar with a lot of the ecosystem changes of people implementing ideas like this in the ecosystem, but nobody had yet sort of done it in an open source way. And so we sort of wanted to pursue that. The reason why we pursued an open source strategy here was because we don't believe in long-term forks. and we don't believe in proprietary implementations on top of Kafka and proprietary extensions. And specifically in this scenario, we didn't want to be the fourth proprietary implementation. It seemed like a sort of losing position. So Inkless is that experiment, just now taken into a more production-ready state of being. We've been working on it for the past several months, and we're very happy with the progress that it's made. And it's serving as sort of a testing ground for the ideas for the KIP. So a lot of the work that we were doing in that is now present in the KIP was design discussions early on, just internally on top of the Inkless code. Now the Inkless code has sort of informed us and figured out which ideas are good and which ideas are bad. Now we can sort of forward that information to the community via the KIP.
That's a really smart way to handle it, because once you accept something in Kafka, it becomes stable API, and you can't really change it afterwards. So in a sense, you're sort of front running that and already hitting all the problems and issues and changing the API as much as you want in a backwards incompatible way. And by the time it gets to Apache Kafka, it's already stable and battle proven. Which leads me to a following question: is this production ready? Like, have you ran workloads against this? Does it work?
Yep. So we are running this thing internally at Ivan. We're handling some non-business critical logs. So we believe it's fairly ready for production. So it has gaps for sure, and some of them are listed on the documentation page. For example, we don't support some APIs, and some defaults needs to be tuned according to the real world usage. So like this is ready to be tried. So let's put it so.
Interesting. Okay, well, I had a short look at the code. I didn't have enough time, but I saw a few things. And I looked at the Postgres batch coordinator. And I looked at like this big SQL function that Ivan wrote, actually. I think he was the author. Can you tell me a little bit how does the sequencing actually work? You said earlier in the conversation that this is done inside of Postgres, and I saw the function, so it does seem like Postgres is the one that locks and determines like what sort of ordering each record is going to have. Can you tell me more about that?
Yeah. So first thing, to not confuse listeners, let's put it so that we already mentioned that batch coordinators would be pluggable. So, and for the KIP that we propose topic-based coordinator. So it will be like totally self-contained inside Kafka, very similar to how, for example, tiered storage metadata works now. There are various reasons behind this, but Kafka governance philosophy. No, let's call it, excuse me, Kafka governance philosophy, let's call it this way. It kind of tends to believe that Kafka needs to be self-contained. So external dependencies are less welcome than maybe in some other Apache projects or generally open source projects. So one notable external dependency was Zookeeper, and now Zookeeper is no more in Kafka. So Kafka is like, to run Kafka, you need Kafka and nothing else. So, and we believe if we bring Postgres as a dependency, it would not be accepted. So that's like, we propose to make them batch coordinator interface, just a pluggable thing so that you can swap implementation to what you need. So we will contribute the reference open source implementation that will be available out of the box. But then, well, imagine that you are hyperscaler that wants to offer Kafka, or already maybe offering Kafka as a service, and you want diskless topics. From the scale effect for you, it's just from this point of view, it's better that you utilize your cloud database that already exists in your cloud. That is way cheaper for you than for your customers. So that's not naming names, but you can imagine there are very scalable and very high throughput, high transaction throughput databases in the cloud. And you can implement the coordinator code that is relying on this database and use this implementation in your offering. So that's a thing. And if we circle back to the Postgres implementation, so we started with Postgres because like the main idea behind this was a development velocity. So developing this topic-based coordinator is, well, we spent several rounds of designing, and we realized that it's not easy. So it requires very careful changes to the like introducing of new interbroker APIs. It requires a very careful design of how you pack the data, how you do snapshots and stuff like this. So if we look from the like very high level, like 10,000 meters, that effectively it tries to turn Kafka into like relational database. So there is a famous duality between log-based systems and databases, like relational databases or any other. So, and effectively, when you implement the topic-based coordinator, you have to implement all the missing parts that exist already in like database like Postgres. So just to save ourselves development velocity, like keep up the speed, we decided let's go with Postgres. So we just picked Postgres as a backend store and also like a code execution environment for the patch coordination. And we in our company we have a quite good expertise on Postgres. We are offering Postgres as a service apart from other stuff. So we could rely on internal expertise and like scale it well and configure it well to handle good loads. Yeah, and back to the original question about sorry for the long step back to the original question of how it works now. So you mentioned that there are big functions implemented in Postgres SQL dialect. The main idea behind these functions is that to save network round trips from Java code to Postgres. So we care for these milliseconds, tiny milliseconds that make the difference. So, and if you have to do like 1,000 round trips to commit one file, that's, well, hardly acceptable. So we have to just pack all our logic into SQL functions and ship them inside Postgres to like do one round trip and execute everything inside Postgres and save lots of time on this. So it's fairly idiomatic Postgres with mostly declarative, but with some imperative things like loops, for example, which is very naturally maps to like if you commit a series of batches, doing a bunch of checks and a bunch of like assignment logic on them, you just go one by one and apply all the logic to each of them.
Got it. Okay, I'll try to keep it brief about Postgres because I can probably have a whole podcast just on that. But the other thing that's on my mind when I think about Postgres is like there's one node accepting the write only, right? Is that backed by anything? What happens if that node like completely disappears?
Yeah. Well, there is a replication solutions for Postgres, so you can make highly available setup that doesn't lose your data. You can have like synchronous replication if this is like really a concern. So yeah, there are backups of pretty much everything. Like I mean, Postgres is a backbone for like millions of enterprises around the world. So it's quite reliable. And like, I mean, Postgres plus its ecosystem, like there is, Patroni, HA solution and stuff like this.
Yeah, makes sense. Okay, that's really cool. And I mean, let's talk a little bit about the topic-based solution, then I know the KIP isn't ready, and I don't expect you to talk in too much detail about it, but at a high level, how are you thinking about that? What's the difference there compared to like a Postgres solution?
I think we were very heavily inspired by the way that the excuse me, group coordinator works, sort of following the patterns that have been established before us. And in that sort of model, you rely on your state being persisted in a Kafka topic, and the machine that is responsible for reading and in particular writing to that topic is the leader of that topic. So in the group coordination protocol, if you wish to commit consumer offsets, then you talk to the leader of that partition that contains your offsets. That leader will then persist that into the topic and respond to you in a reasonable amount of time. We think that same model can be used for batch coordination, just with the structure of the, not the structure, but the contents of the topic swapped out for batch coordinates and all of the necessary metadata, and with the actual operations in the leader being changed. So instead of writing batch coordinate, instead of writing consumer offsets, you're doing the leader operations, you're assigning offsets and such.
Got it. Okay. And what is this thing about being backed by a KRaft quorum? Is that also something you're exploring?
Yeah, so we that was the first idea, where to store metadata. So let's start it in KRaft. Problem being is that this will require changes to KRaft. I wouldn't say fundamental, but quite a bit of changes. KRaft heavily depends on snapshotting. And these snapshots, they are, well, you can imagine what KRaft stores, like topic configurations and like a cluster membership, and like, so it's volume of the metadata is, well, megabytes or maybe hundreds of megabytes, but not hundreds of gigabytes, for example, as we might expect in highly loaded Diskless setup. So, and how it's currently implemented is just not ready for this. So like if you make a 100 gigabyte snapshot, and this will be tried to send over network in one request, so this will never fly. So of course, I mean, Raft would be a good medium for this because, well, it's Raft. It can store data reliably. It can like elect leaders and stuff like this. But to make it work, there are lots of changes I needed. So we were not ready to do this, and then we realized that we probably don't need to rely on Craft, and we can just rely on external implementation, external from the controller part of Kafka. And this will just work as well.
Got it. And then, I mean, you probably don't have a great answer to this because we're still sort of discussing the KIPs, but give me some pros and cons of each setup. Like what you said, Greg, you said that like object store is the most pure. But if I have to ask you, like, what do you think scales the best? Or like, you know, if you had like 3 years to work on this, how would you do it? Like, what's your favorite?
Personally, my favorite is the Kafka based one, just because I think it sort of slots into the existing sort of design patterns of Kafka pretty well, and because we've seen that the scalability of Kafka topics is very high, like just classic Kafka topics. And so if you consider that we can get away with essentially like having a Kafka topic that only contains the metadata is only a 10th or a 100th or a 1,000th the size of the actual data being handled, that means that we can get away with a 10th or a 100th or a 1,000th the number of classic topics just to handle the metadata. I think it also has really good properties for scaling. So similar to how we were talking about having multiple leaders, multiple batch coordinators, the Kafka topic-based solution sort of fits very naturally into that because you can just have multiple partitions within this batch coordinator topic, and you can shard out the load not exactly like, but very similar to the way that consumer consumer offsets is handled. It does have some complexities and some downsides, and that's why we're still like working on it to sort of resolve those things and actually implement it. But I do think like given time, I think that will turn out to be one of the best implementations.
Yeah, I agree with Greg. So we all think that's a way forward, but it just takes time to implement properly. So Kafka, currently you can take the Kafka Docker image and you can start fully functional cluster. And this is a nice quality to preserve. So we should try to preserve it.
Yeah, nice. Okay, makes sense. Yeah, last question about the coordinator then. Like, it seems to me that this has the potential to become the bottleneck in a Kafka cluster. If every broker, let's say we have 100 brokers accepting writes and committing batches, like all of these requests go to potentially one coordinator, potentially more if we partition it. Like, are you scared of that becoming a bottleneck? Like, how do you think that gets sort of alleviated, or is the work lightweight enough that maybe like a vertically scaled up machine can handle everything?
I think it
Yeah.
remains to be seen. I think we have to do some more planning for it. I don't. It definitely will be a bottleneck, such that there will be a user at a scale that cannot be served by a single batch coordinator. Like that customer already exists in the classic topic space, and so I expect that we will very quickly run into them in the diskless topic space. So I believe that we do need a story about partitioning the load and sharding the work in the coordinator. There will be an ultimate limit to it. But at the same time, I do expect that you can get away with a lot off of a handful of coordinators. Like for example, I don't expect in the next 10 years to see 1,000 coordinator cluster. Maybe I'll eat my words, but it'll be 10 years from now. I'm expecting sort of in the 5 to 20 coordinator range for like the largest clusters today, just sort of pulling numbers out of the air.
Yes. So nothing handles infinite load, not even S3. So it's just a matter like find what's a practical load ranges that exist in real world and serve them with reasonable design.
Makes sense. I like the sound of that. Yeah. All right. Well, we covered the right path. We covered the coordinator in that. Can you talk to me a little bit about the rates?
Yeah, sure. So on the read side, essentially the first thing that a broker does when it receives a fetch request is it needs to collect the metadata to answer that fetch request. So it needs to know where the current offsets are for the topics. It needs to know where the batches are that actually contain the data. And all of this information is stored in the batch coordinator. So all of those batch metadata that we wrote into the batch coordinator in the produce step now has to get queried and retrieved for the fetch step. So the broker will make a request out to the batch coordinator. The batch coordinator will collect all of the relevant batch data such that the broker can then sort of serve the fetch request. And the broker, once receiving this metadata, now has a map of all of the partitions that were requested for that client. It has a map of where the data actually is in the objects, which objects contain that data, and it has enough information to start making requests out to the object storage. At this point, the broker can issue those requests and wait for them to complete. Once all of the data from object storage has been loaded into memory, the broker is able to sort of slice and dice all of the requested objects into the actual final data that needs to get sent to the consumer. And the sort of final step that was left over from the produce step is that it actually has to inject the offsets from the metadata back into the data. So the data that was in the object was write ahead data. It didn't have any offsets in it. It didn't have any timestamps, for example, in some situations. And the batch metadata does have that. It just combines the two in the format that the consumer expects and then serves the fetch request.
Interesting. I have a lot of questions after this. Okay, so fetch request comes in, and let's say it asks for data for 100 partitions from a given offset. And let's say this is the pathological case, and this data exists in 100 objects in S3. Actually, it can even exist in more objects, maybe, but let's say 100 objects. So in this model, you have the broker have to issue, I guess, 100 GET requests to S3. The S3 request here you're using is a byte range to get, so meaning you're only reading a particular part from a big S3 file. Is that a problem?
That is a problem.
It's the problem.
The problem, yeah. Yeah, of course, each connection to S3. So S3 is just HTTP interface. So you can open a fair amount of these connections, but you probably don't want 1,000 anyway. So if you start pulling, you start laying these requests in queues, so the latency grows. So basically the question how to reduce the number of connections that you, or GET requests that you need to issue. So, and that comes to the one topic that we haven't covered yet, haven't touched yet, which is, it doesn't have still a right name, which we try to figure out, but let's call it object merging. So we said we upload by 1 megabyte or 8 megabyte, depends on your configuration, something like this. But these files, they don't have to be that small forever. So on object storage files, objects, they are immutable. You cannot override, but you can download them in the background, merge them into one huge blob, and upload this blob. And atomically, well, thanks to the batch coordinator, you can atomically swap the original 100 files or whatever number with the one file that you get on the output. In this case, if you, for example, sort, if you group batches by their partitions and sort them in order, you don't have to open many requests. You can have limited number, less than before. In the worst case, you open. No, not in the worst case. In the best case, you send one GET request per one partition in the fetch request. And there are also optimizations. So if you know that these partitions are in the same file, you can see, okay, maybe they are adjacent. Maybe there is a tiny volume of data between them. We can just get one stream of data from the object storage and throw away what's irrelevant and keep the relevant part. Because data transfer is free to and from object storage. And from latency perspective, it might be better to download more data than to send two requests instead of one.
Well, there's a lot of things here. But also, I want to remind readers that actually even Kafka today with tiered storage doesn't send more than one or a few GET requests for a fetch request. So if a fetch request comes to a Kafka broker and it asks for historical data that's only present in S3 because you've used tiered storage, the broker is only going to serve one partition out of that whole fetch request via S3, and the rest is going to return nothing, and you have to send another request. So to an extent, there is this precedent in Kafka where if you're trying to read a lot from a historical store like S3, you can't really expect to read 100 partitions at once. Yep. But even if, for example, I assume you don't have this limitation yet, again, 100 GET requests to even one S3 object, it still feels like a lot to me. Or even if you do a big byte range to get in, you delete some stuff, then you're reading too much. But again, is there any caching? That's sort of what I'm driving towards in the read path.
Yeah, caching is a large part of this problem. So even if we did sort of do the ideal merge, and you can get a big chunk of data for a single partition all at once in one request. If you have multiple consumers reading that data, you'll issue a new GET request each time a new consumer comes in. And for typical Kafka deployments, it's not always going to be a single consumer on a single partition. It can be multiple consumers. That's sort of the model of Kafka. So there is a strong need for caching, just like in classic topics where they made use of the page cache. Diskless needs a cache as well, but it can no longer use the page cache anymore because we're not using disks. So the model that we are exploring in Inkless right now is a distributed cache inside of each zone. So what does that mean? That means that all of the brokers that are in a single zone form a single sort of logical cache. And all of those brokers can request cache data from one another, and they all sort of collectively assign memory that is able to be used to cache blocks of data that are read from object storage. And what this means is that rather than your fetch request resulting in 100 GET requests or even 10 GET requests, it's going to result in like enough requests to load the data, and then all of the sort of irrelevant data that was loaded along with your request is cached and able to serve all of the other fetch requests. So your first fetch request is still expensive. This is the classic story with caching. But your next fetch request for the same data, your next fetch request for nearby data is much, much cheaper. You can get, you basically get it for free just for the cost of memory.
Got it. And I also saw in the Inkless code that you cache on write too. So when you're writing, the broker that's writing that object gets stored in the zone that the broker is in. Is that right?
Yeah, that's a really fun sort of optimization. So there's if you write in one zone, you could, if you didn't have sort of explicit cache warming, when you have when you have a consumer in that same zone, it might have to just go read the data that it just wrote into object storage. And so we can eliminate 1/3 of all fetch requests by just having the produce, in addition to writing to object storage, also write into the cache. So it's sort of self-cache warming, but just in a single zone. The other zones that we're not actively sending data to, that we can't replicate data to directly due to cost reasons, they still have to make the fetch request and then cache the data. But at least the producers in the local zone have very, very efficient use of the cache.
But does that actually cache you the whole fetch request? Because if we try to run to a simple example, let's say we have partition 1, and you have producers in every zone sort of writing to partition 1. So you have, like, let's say offset 0 to 50 written in zone 1, offset 50 to 100 zone 2, 100 to 150 zone 3. You know, a consumer might read out 3 of these at once, or maybe just reading some other partition that was written in zone 2, for example, assuming the consumer is in zone 1. So in a way, I imagine maybe you never actually get to catch the whole request. How do you think about it?
So, well, first thing is that we're not just, well, maybe detailed, but still, that we're not caching the response to the fetch request in total. So we chop it in chunks and cache these chunks. But then, yeah, that's absolutely possible that you can, like you pre-warm the cache on one zone and you read from a different zone, and you don't hit the originally pre-warmed cache. So that's possible. Yeah, there's, of course, there might be strategies to get around this. So you could signal to other zones that, okay, guys, I have this new data that is hot, and you might work to might want to pre-warm your caches with it. So that's possible. That's actually, yeah, please, Craig.
Yeah, I think your question was more getting at like if you have producers in multiple zones that have to all arrive in the same in one of the zones, then you still need 3 requests essentially. You need the write and the 2 reads. And that is definitely true. Like in order to serve a fetch request for a single partition, you would need to read those 3 objects separately. You can't have a S3 request that reads multiple objects. But the idea is that at the time that you issue these requests, they are also loading data for other partitions. And so that single request, all of that sort of bycatch data, all of the stuff that isn't immediately relevant to you is still cached and can be useful for other partitions. And in exactly the opposite way, if another consumer makes a fetch request that just happens to land near the data that you need, it will cache it, and then you only have to make one request, for example. So the fact that it's a distributed cache, all of the brokers in a zone are working together, and the data loading is happening on larger chunks, like larger than a single batch, larger than a single partition. That enables you to like get this on aggregate better behavior, even though the single request is sort of just as expensive in isolation.
Right.
And there is another angle to this story, which is prefetching. So luckily we are in Kafka and we are reading logs, and logs tend to be read in sequence. So, and we can exploit this and pre-warm cache as we read. So like we hit one offset, we serve this fetch request, but we also read ahead and grab like a couple of megabytes of, or maybe multiple megabytes of data and store them in our like zone local cache. So the next request will be served faster. This, for example, you can do it like an operation system. When you read files, you can instruct, or at least like the POSIX operation systems, that I read this piece in the file and I will be reading it sequentially after that. So the operation system, like the disk block device driver, it will prefetch data from, store it in page cache for you. So same idea applies here. So logs are read sequentially. So we could, okay, I'm reading 100 offsets in this request, and very likely that I will read 100 of offsets in like a second after that. So we could initiate the fetching earlier and then serve the subsequent fetch requests as fast. This one we haven't explored yet, but this is like good possibility.
I saw you do that in your tiered storage plugin, and I thought it was really smart. It's a really good point that, if a consumer in one zone is reading offset 100, it's probably gonna send you a request for offset 200, soon enough. So I think that's really smart. Yeah, okay. So this is the caching and the reading. You mentioned the merging of objects. So again, data comes into brokers, the brokers batch it, and they write these batches into S3. And basically you get an S3 that has like a lot of objects. What was it? 250 milliseconds per batch, which means every broker is uploading 4 a second, which means every minute you have like, how many? Like 240 a broker. How does the merging work? Like how often is the merging done, and what is the end result of the merge?
Yeah. Well, I can take this. So, all the intervals and all the stuff, they're configurable, of course. So the idea, why do we need merging? So first, we already discussed, the first point is that we want fewer files, less fetching. We want to fetch in bigger chunks. So to fetch in bigger chunks, we need to remember Windows 95 and defragmentation thing. So that's pretty much the whole same idea. So we want to defragment our data on the remote storage. We want consequence sequencing batches to like lump them into like together in a contiguous like ranges of data in the same file or different files. So that's first thing. Second thing is that I mentioned some time ago that we have 100 bytes, about 100 bytes of metadata per batch. So, which means that if you do some calculations at 100 megabytes per second, in 1 month we'll have 24 gigabytes of metadata for these batches, if batches are 1 kilobyte in size. And there will be like 200 something billion of these batches, which is quite a lot. But if we, for example, merge neighbor batches into bigger batches, this Kafka allows to do this. This is not a violation of any Kafka guarantees. So you have kilobyte size batches, 1,000 of them. Here you have a huge megabyte batch, contiguous. So, and you slash your metadata by 1,000 easily. So that's a second operation that we can do on file merging. So we not only rearrange batches closer to one another, but we also merge them together to like just reduce the pressure from the metadata side. The third thing that we have is that, well, Kafka has compaction, right? So to compact, compacted topics where like you have keys and by key you override old values. So this, like Kafka, basically how it works in classic topics, it reads segments and it creates new segment based on data that is read from the previously from old segments, and then old segments are discarded and the new segment is written instead of those. So same idea here. We need to rewrite batches, replace one record with another one to preserve this semantics of compacted topics. So that's number 3. Number 4, I forgot. Yeah, I have 4 or 5 things.
Okay,
But
they'll,
well,
they'll come.
that's 3 already enough.
They'll come to
Oh
you as
yeah,
you ask
sorry.
more.
I remember. So imagine that you have whatever data in your topics, and now, for example, you have sensitive data like customer data, and there's some like personal information protection legislation like GDPR or something like this. So you delete this data. But when you delete, you cannot delete data from object in an object storage, right? It's just a mutable blob of data. So you delete it logically. So you delete the batch metadata from the coordinator. So this batch is dead, and it's just kind of marked as a deleted from the file. But the data is still there. So, for example, GDPR enforces 30 days of like deletion period. So you have after the like customer or like how it's called like subject of personal information, when the person files a delete request, you have 1 month to physically delete it from all your backups from like everywhere. There are tricks to go get around this with like per person encryption, stuff like this. But in here, like we have effectively we get objects with garbage, like in garbage collection in Java, for example. So this batch is dead, this batch is dead, and eventually you get like a megabyte. Like maybe if you do compaction, we have like 100 megabyte file with only one batch inside this file, keeping actual live data, and the rest is just garbage. So we need to, what do we do? We need to evacuate this batch to some live file, and this is rest is garbage that we discard. But again, if I can bring analogy, this resembles a garbage collection in like it's regional evacuational garbage collector in Java, like G1 on some similar. So you take the live data, relocate to a new file, and then the rest is just garbage that you throw away. So that's a 4th reason to do object. Well, like actually we've been pushed back on the compaction name because compaction exists in like other context in Kafka, that there is a like topic compaction, and so it's like very confusing when I speak like topic compaction versus object compaction. So we have to come up with better name, but
Right. You call it
let's call it so.
compaction. I called it merging. That's why I
Yeah,
call it
merchant
merging.
maybe
It's,
is better. So
And listeners, if you have your own ideas, throw them on the KIP.
yeah, please.
yeah,
Oh
please.
yeah, we should actually have said this in the very beginning of the podcast, that these KIP discussions, they are in the Kafka developer mailing list. So everything happens in the open. Please do come if you have questions, ideas. Do come to the mailing list. Find the relevant thread from the archive. Google will help you. Send your questions. Don't use the KIP page on Confluence, because it's it's never read and no one uses it.
Right. Yeah, I feel like that's what I'm doing here. I feel like this podcast is just like one big email of questions by me.
Oh, yeah.
So thank you for answering them. But yeah, continuing on that, so we have the merging. I call it merging. So you basically get all of these small files that you have throughout some time period. You said it's configurable, and you merge it into one bigger one. Now, I want to ask about the intervals as well, like how often it happens, how big is a new file. But to get to that answer, I need to ask: is the new file per partition, or is it again like a mixed file that has like a lot of partitions in it?
So that's a difficult question, because the answer is we haven't decided yet. That there are pros and cons on both approaches. So to like maybe expand a bit what you said, it's like originally we upload like we call them shared segments, so shared segment objects, where data from multiple partitions are in the same file, in one file. But question is being like, when we do rearrangement and merging and whatnot, should we keep the original Kafka classic topics approach, where all the data for like one file has data only for single partition? Or we should just have the same approach with multiple partitions, just bigger? So the benefit of having separate files per partition is that, for example, compaction and time-based, size-based retention becomes way easier. You don't have to, like, you will have to relocate data way less, because, well, you're not constrained by other partitions. You have only one partition, and everything happens inside it with its own configurations. But the downside is that, well, you have to do proportionally more put requests when you do merging. So if you have 1,000 partitions in one logical big file, you have to do 1,000 put requests. So we haven't decided. We haven't heard from the community. Well, let's see. The like exploitation of the system in the life will show.
Yeah, I think we're really struggling with like the just the vast variety of shapes of data that people put through Kafka today. I think that there are situations where a shared segment makes sense as an output of merging. I think there are scenarios where the individual partitions make sense. I could see actually both happening at the same time. So, for example, if you have a very large partition, you would want to separate it out so that you can sort of get individual objects. But then if you have a ton of really small partitions, like just keep it together in the same segment.
Yep.
I think that once we like really start seeing how people are using it, we can make some more informed decisions and even make it configurable to say like, hey, here's a merge policy, for example. All of that I think is to come in the ecosystem. I think that everybody is going to be able to have a lot of input on this and customize it in the future.
Yeah,
very interesting.
But luckily we can change this because it's like broker side thing. So if we figure out that with time that this particular policy does not work, we can change it in subsequent releases, and Kafka just becomes better, and you don't have to upgrade anything on your client side, which is usually much more difficult than just upgrading the new version of the broker.
Nice. That's really interesting. I had a question related to reading, but also to merging. You said that on read, the broker reads the data from S3 and then talks to the batch coordinator to get the offsets and then combines both of those and then returns the response. Now, this makes sense to me because the first object you upload to S3 doesn't have an offset, it comes later. But at the time of merging, allegedly, you already have offsets for everything that you're merging. So is there a reason why you can't just put the offsets in the merged file and just return the data directly when you're reading historical?
Yeah, I guess you can. But will this be better anyhow otherwise? That's a question, because to get files where you read from, objects, you have to contact the batch coordinator, and batch coordinator could as well return the offsets to you in the same response.
Yeah,
You
I would
probably
say,
save some data modification on the broker side, but
yeah, architecturally it's exactly the same. Like the only difference is whether or not you're mutating the like memory buffer before you send it out. And I don't see that being a very big bottleneck. It's a very reasonable like optimization. But at the same time, it's because you when you're reading data out of the cache, when you're reading data from objects, you may not know whether it has like had offsets put into it. It's just always safer to assign offsets regardless. There's no danger of sort of returning an unordered batch back to the consumer. But with enough like good bookkeeping and like implementation, like we can make that optimization.
Got it. And Ivan, you were saying that when the broker asks the batch coordinator, hey, where do these offsets live? You're basically saying it can tell you exactly, like it can respond, hey, it's this byte range in this S3 file, these offsets are there. And that's why it's not like an extra round trip.
Yeah.
And in the cache?
It probably can be cached, yes. So, but here comes like cache consistency is an interesting problem and challenging one. And why I'm so concerned about consistency of caches here is that Kafka has certain guarantees. So, for example, if you use classic topics, you produce some data, you read this data, then you truncate this partition. So you can delete a bunch of old data just by request, not by policy, but just send your request, delete like 90% of the data. And after that, next request will not read the deleted data because it's deleted. So Kafka gives strong guarantees of this. So like it remains an open question, like how much we want to bend these guarantees with Diskless topics. So for example, if we cache batch metadata on the broker side, we get faster responses, but we might serve data that could not be already servable. Or like you see what I mean, right? So you could another like a request can come to another broker, delete a tail of this partition, but on your original broker, this tail is still cached in the metadata cache locally. So is it a violation of Kafka guarantees or not? Well, formally it is, but is it should we follow the formalism, or should we follow the practical value? That remains to be seen, remains to be discussed with the community.
That's difficult. I guess that's why they say there's like hard things in computer science, like naming things, off by one errors, cache invalidation, and exactly once.
Exactly.
All right. Well, I want to address the elephant in the room. There's like this big elephant in this room. It might be pink, and that's called like latency. Obviously, latency is gonna be higher. We have brokers waiting for 250 milliseconds. We have S3 puts that have like multiple hundreds of milliseconds of latency. You have the batch coordinator. You have reads as well that come from S3. First of all, like, what's the latency you've seen in the system so far?
So, well, we've seen crazy latencies, but when it was in development. So, But yeah, you're absolutely right that latencies, like produce latencies and consume latencies, they will grow. You correctly outlined the three main contributor to the produce latency, which is like original, let's say again 250 milliseconds configurable wait period. So in the worst case, in average case, you wait half of this. In the worst case, you wait full. But then you need to upload the data to, well, S3. We always pick S3, but it should be read as, heard as object storage. So it takes also, like, depends on the size and also on the storage class that you're using. So it might be several hundred, well, 1 or 200 milliseconds. And then you need to commit this with the object coordinator, which is the fastest operation. And for example, on Postgres, we've seen like 40, 50 millisecond for big files, like, I mean, with lots of batches.
That's like P99?
Well, I cannot say now, but most likely yes. Like I can check with our.
I think we've been
drafts.
focusing on the P99s, yeah.
Yeah, P99 is a thing.
So total latency?
So two round trips for the producer, plus linger MS on the producer side, plus accumulation period, upload period, and commit. So together might be, for example, a couple of seconds.
Got it. Yeah, I think people don't really count the linger. Okay, so latency could be a couple of seconds in P99, you say. Like if I try to run the numbers myself, it seems like the ideal system should be able to do it like in a second or something. Do you think that's possible? Like 1.5 seconds, let's say P99 end to end?
Yeah. So there are ways to reduce this. For example, we can upload to S3 at the same time as we wait for more data to come. So we don't accumulate the buffer and memory. We upload this to S3 as fast as it comes. So there is a multi-part upload, but here is a trick that multi-part, the minimum part size is 5 megabytes, again on S3. So you cannot upload every bit. You need to still in the best you can reduce the latency maybe 2 times. That you upload the first part and then another part. But there are other ways to, like creative ways of using S3, which we haven't tried yet. But you can declare the size. Like to upload a file in one go, you need to declare the size of it in advance. So you can say that, okay, I have up to my configured limit, 8 megabytes or something. So I will upload a padded file with, it will contain batches and it has a tail of the file will be zeros. In this case, you can upload as we receive the data, just like, well, down the everything. There's just HTTP connection with chunked encoding, with the data going in chunked encoding. And we, from the broker side, we can send chunks as we receive them from the producers. So this optimization is promising, but we haven't tried to implement this.
Yeah, I think there's lots of there's lots of creative stuff that we can do. And by creative, I mean more complicated, more error prone, more unreliable. Right now we have sort of like the pure implementation. There's not really any tricks going on. But I think even within the current implementation we have, like we do expect people to be able to tune this and get the latency down sort of theoretically as much as they want. Practically, like there is going to be like a lower limit. So what that means for us is that if you tune your batching size, like the amount of time that the broker spends accumulating, if you tune that downward, you can get more commits per second, which means each commit will happen at a lower latency. You can obviously reduce the linger MS and get worse batching, and that's going to come at a throughput cost. And you can also optimize latency somewhat. So if you have your batch coordinator close by rather than being in another region or something, there's still like optimizations needed on the sort of user side, deployment side, configurability side. And there is sort of going to be a fundamental lower limit where the cost becomes prohibitive.
Got it.
So yeah.
Yeah, makes sense. The cost becomes prohibitive. You're saying because the more often you batch in the broker, the more often you upload objects, the higher the cost.
Yeah, the magic in object storage is that you need to make large requests, and the reason for that is because you pay for the data that you're getting, but you're also paying for the actual like request itself, and so the number of requests you ultimately make is just the opposite or the inverse of how much data each request is grabbing. So the inflection point seems to be like around a half megabyte or a megabyte. So if your objects are under a megabyte or so, you can actually end up with a less cost-effective cluster than a classic topic cluster in some scenarios. And that is sort of like the single inflection point you have to worry about. Now that if you if you're really concerned about latency but still want diskless, you can tune it down so you get down to like a megabyte or a half megabyte. But there is going to be a point where you're not going to be able to get any more. Your price is going to double, and you're going to get like 10 less milliseconds, and it's just not going to be worth it.
Got it. Yeah, I pulled up my calculator actually because I created a calculator exactly for this to sort of tell you the break-even point of at what like batch interval does the classic solution tend to cost more than the replication. We have to dive into costs soon enough, but so basically what we're seeing here is at a very high level. We can move the discussion to a higher level. You see, like the slower your topics are, the higher your latency is, the lower your cost is going to be. And if you want it to be really fast, then you're gonna have to pay up. Either you're gonna have to pay more because you're tuning your batch interval to be smaller in this direct to S3 design, or you're gonna need to use the classic Kafka with its low latency. That's even more expensive. So I want to ask you, from your experience as Kafka practitioners throughout all of these years, what do you think people actually want from latency? Like how many of the use cases do you think like work well like at latency that's maybe P99 of a second or like 2 seconds? And how many do you think need like strict below 100 millisecond P99 or anything in between? I know you've worked at Ivan, probably other places before, so you've seen a lot. So what do you think?
Yeah. So yeah, like we spoke with our customers, we spoke with people in the industry who are Kafka users, and that's surprising how many use cases and Kafka users don't need sub-second latency. Let's imagine like any use case that rotates around physical world. So you are ordering something from a web shop. If the delivery time to you as a user is a couple of days or even a couple of hours, do you care if this request comes from your click to the all the relevant microservices in 100 millisecond or in 2 seconds? You probably, most likely, you will not know. Or if we get away from the physical world and say you're pumping metrics and logs through Kafka, through these topics, you probably, in some cases, you want fast metric delivery. So even a second would be problematic. But in most cases, you're fine. So 2 seconds, anyway, you're showing in Grafana with like 30 seconds interval. So and if you deliver a couple of seconds later than the event happens, that's not a big deal. Unless you're doing real-time, like fraud detection, for example, which is obviously can work only with classic Kafka topics and not maybe even just classic topics, but for example, backed by in-memory disks to reduce latency even more.
I would also say that though we're comparing and contrasting Diskless and Classic and calling Classic like the low latency solution, really maybe it's more accurate to call it like a medium latency solution, because there are more like or lower latency solutions in the broader ecosystem. Like you can just skip the whole Kafka thing and make direct network connections if you truly have latency. So like if you are in a quant trading firm, maybe you need sufficiently, like if you really, really need low latency, you're not going to use Kafka in the hot path. And so I think by virtue of being sort of a medium latency product, so far, Kafka has encouraged users to push their lowest latency stuff out of Kafka. And so there's a lot of opportunity for the higher latency Kafka to really make very, very strong inroads. And it's going to make inroads only like based on the cost savings. I truly think that Kafka itself is most valuable as an abstraction and a way of thinking and a way of promoting good scalability and design. And that comes with a little bit higher latency. People are okay with that. And if it comes with even increased latency, but at a steep cost savings, I mean, again, just pulling numbers out of the air, I feel like this can make a huge impact on every single user of Kafka. And even within each user of Kafka, I think it can make a big impact on more than 50, more than 80% of use cases. Yep. I think it has extremely, extremely wide applicability.
Yeah. So not only transforms existing use cases, but it also like enables new ones for which like classical topic is just impractical. So before that, like should we put this 100 megabyte per second workload through Kafka? Maybe not. It won't bring us more money, more value for the company than we spend on supporting this workload. But now the points shift to the left, and we say, okay, like, why don't we log every event in this particular thing that we happen to have in our system that we can analyze later and, for example, run machine learning after that. So that's enabler for new stuff.
Got it. Yeah. I think the scariest part of this hour is that I agree 100% with you. I think I want to run through some examples too. For example, like I definitely agree with you, Greg. Like Kafka, the protocol is not made for ultra low latency. If you truly are obsessed with latency and you want every request to be under 5 milliseconds, let's say, you're not gonna use Kafka. Even under 10 milliseconds, it gets kind of difficult. You have, Red Panda that also advertises low latencies, but at the end of the day, they also use the Kafka protocol. So maybe they can get lower latency than Kafka due to some bottlenecks. But at some point, for the ultra low latency, I assume the trading firms where every millisecond or microsecond matters, they won't use Kafka. And then, like I think also as an industry, I have to assume that we've become a little bit complacent. I have to assume this comes from the zero interest rate policy that we had for 10 years at the time where Kafka was created and everybody started moving to big data. And I think like this idea of ultra low latency, real time was really pushed onto us by a narrative, really, that you have to be ultra real time. You have to like react the second something happens. Not the second, you have to react the millisecond something happens. But like even a low latency use case I can think of, something like an Uber. Okay, so I live in Spain, and here we don't really have Uber, at least in my city. We have like some other apps, and the driver location updates, but it doesn't update every second. It's kind of like a little bit slow, like maybe every 5 seconds. And most of the time, you think that's the real-time latency use case, but I'm fine with updating every 5 seconds or every 2 seconds. It's not like, he's probably waiting at the traffic light for 60 seconds. He's driving at 50 kilometers a second. It doesn't really matter if the time is like, it's slow by 3 seconds or something. I think the fact that we now have this lever to enable diskless topics and get the cost down, and we're going to talk about cost, but the cost is close to 8 times cheaper than regular Kafka. I think that's really going to force everyone to sort of ask themselves the hard question, like, do we really need classic topics? Or, we can pay 8 times less and get like, okay, a second latency, like does my use case actually suffer? Ivan, you said, a lot of times logs and metrics are actually one of the best examples. I think in my last job, we want metrics to come ASAP, but actually we would scrape them every 30 seconds from the machines, because if you scrape the metrics too fast and too often from the machine, that causes issues on that side. So if it's coming every 30 seconds, I'm probably, by the time it reaches the dashboard, it's probably 35, 36 seconds, whatever. Does it really matter if we put an extra second or two there, if we can get the cost down by 8x? We know that observability in a lot of companies is a surprisingly big cost item. So I think that's huge too. And of course, we have like the use case of Kafka where you just feed your data lake. I've seen so many of these. I also, like, if you put a gun to my head, I'll probably say that all the gigabytes per second we see people talk about in Kafka, like a huge aggregate of that is probably just people dumping stuff into the data lake. And that is completely latency agnostic, whether it's a second or even a minute. So for that reason, I'm really bullish on Diskless topics. I really think it's going to take the industry by storm. And I like, huge kudos for me for doing this. I'm really happy to see it in the open source, and I really think the impact that your guys' work is going to have on the ecosystem, not only on Kafka, but the data engineering ecosystem, I think is actually very underrated right now. And I think in 5 years time from now, I think we're going to see. So yeah, I also think it's going to be huge. I want to do a devil's advocate, of course. There are times where latency matters. I don't want to be too much into the other extreme. So for example, if you have like a stream processing job, and that stream processing job has like 5, 6, 10 steps, usually, a lot of these steps like consume the data, then they write a new result into a new topic, then they consume again and read. So every step. So if you have like, 5 steps, for example, and every step takes like a second or two, then that does increase, the end-to-end result to 10 seconds. Maybe that's not a problem again, because maybe it's like a use case that actually doesn't suffer that much from latency, doesn't care. How much of this have you seen? Like how big is stream processing in your eyes and what you've seen? And also, do you think that's probably like, a fair amount of use cases?
I mean, I really want stream processing to sort of be the future of Kafka. I want people to be able to write applications reading and writing directly from Kafka. I'm very optimistic overall. And there's enough users right now that these sort of multi-stage applications are important to support. And I think that's one of the big motivations for us calling this diskless topics and not diskless clusters. We made the distinction that this is a per topic enablement, and we are not in any way eliminating all of the existing work that's been done on classic topics. I think that's a mistake that actually some of the other competitors in the space made, is that they wanted to enable this on the cluster level. And by doing so, they make their users choose high latency, low latency ahead of time, and really close the door on these situations where latency stacks up quicker than you want, or where you have applications that need to write and read low latency data, but then there's another application that just needs to read it slowly and write it slowly. So with diskless topics, like I said earlier, I think that everybody will get a benefit out of it, but only 80% of use cases might. That's what I mean by maybe there's 80% of topics, or 80% of the data is in diskless topics. And then wherever diskless latency doesn't make sense, you're not obligated to incur that higher latency. You can just choose not to. I think that flexibility is really like the winning move for this sort of feature.
Yeah, I agree. I think that's huge. So if we try to do a lay of the land, we have Warp Stream, we have Buff Stream, we have Confluent Freight, we have AutoMQ, and some other non-Kafka systems, I guess. And all of them, I think, force you to just choose one deployment model. And some of them are only S3, which means you can only choose, like, you have slow topics if you want. And I think that's a huge problem, actually. I'm so surprised that Kafka is kind of the cutting edge. It's going to be the cutting edge here. It's going to support both. It's going to support before any of these proprietary.
I do find it very,
features.
very surprising, especially because I think some of those implementations are based on the Kafka code base itself, and so there's no reason theoretically they couldn't do what we're doing. There are other ones where they threw out the whole code base. That's like the C++ and Go implementations. And so they would have to sort of work backwards to get to classic topics, whereas we are just extending. But yes, I am surprised that everybody else made that mistake. And so I worry that like maybe we're making the opposite mistake, but I feel pretty confident about it.
Yeah, because to pick up on this theme, that I'm pretty happy that we, well, apart from open sourcing and everything, upstreaming, I'm pretty happy that we built this on top of Kafka code base. The amount of code that, like, not even like pieces of code, but existing functionality that we reuse and don't have to re-implement is enormous. So in our blog, we claim that we used 1.7%. It may be 2-3 more when we implement everything. But still, it's like we're staying on the shoulders of the giant and not having to re-implement. Like take alone, take the test suite alone. So that's like hundreds of thousand lines of code that test the cluster and all the pieces of functionality comprehensively. So imagine porting this to whatever language apart from JVM.
It's 500,000. It's 500,000 at least. Last time I looked.
Yeah, it's like 25 or 30,000 tests. Like that. Yeah, that alone makes it like an incredibly strong reason to use like Java. But the other components, like not having to re-implement metadata. I mean, it's taken us how many years to replace Zookeeper, and then do you want to turn around and throw it out again? I don't think that makes sense. The existing group coordinator, none of that had to change. Like,
yeah,
the amount of code reuse is staggering.
And that is complex code, by the way. Like it's really easy to get a consensus algorithm wrong. It's really easy to get the consumer group protocol wrong.
Yeah.
And I think that speaks a lot to your velocity, because I opened the Inkless repo yesterday and I saw 4 people as the contributors. I don't know if I'm wrong, but the main contributors were 4 people, the most amount of commits. It was you two, it was Joseph, and Jorge. And the first commit I see, the commits picked up in November 2024. Today is May 2025, so it means that you have a production or almost production ready version in only 7 months. Is that accurate?
Yep, that's about it.
We had discussions like I think a year and a half ago, roughly. Maybe it's almost 2 years now. Just sort of like piloting the idea, but not writing any code. But yeah, the implementation on what we have today only started in earnest in November, and we were a very lean team to start. So I think I was the only one working on it for the first 2 months, roughly, and then Jorge and Ivan joined, and so it really is amazing what we've been able to do with a very limited amount of like work hours. And that is like honestly like the winning element of open source is being able to extend these things, is able to develop on top of it. And the phrase stand on the shoulders of giants is trite, but so accurate in this case.
Yeah, I think there's a lot more to the open source. I mean, Philip, the head of streaming at Ivan, like said it in the blog post, but some of the other benefits that come to my mind is like, you ship this and then it goes to every Kafka user immediately. There's no need to adopt you. There's no need to renegotiate a contract or whatever. It's not even a new cluster type. It's just the new version of Kafka. That's the distribution that you have to open source is crazy. It is huge. So I mean, I guess we can segue to the open source a little bit. I still want to ask about latencies and costs and operation, but so this is still like a KIP. It's still being discussed. Do you actually think it's gonna get voted in? Like, do you think there's a chance people don't accept this?
Well, there are two more competing proposals. Well, competing is maybe not the right word, but they operate in the roughly same domain and solve roughly the same problems with bit different set of trade-offs. Let's put it so. So, and we hope that all these could coexist in Kafka code base and solve right problems for you be right tool for the problem. But it's not impossible that community decides, okay, we don't need three, we need only one. And it's also not impossible that it be not ours. So, well, the Kafka benefits anyway. So,
So you said the two proposals, so I have them here. One is Slack's KIP-1176, and the other one I think was from AutoMQ. I actually haven't seen the AutoMQ one, but Slack's one, from what I understand, is they use S3 to replicate between the brokers. They keep disks, they keep leaders. So the only thing that happens is sort of the replication path gets a little bit cheaper. What do you think about that? Is that I haven't commented on that mailing list. I thought I think this can actually live with Diskless, and I think you can have both. This sort of optimizes for the Axe1 produce request, which I guess we can talk a little bit about it here and how your proposal works with that too.
Yeah, I think they're without sort of going into too much detail here because I don't want to misrepresent anybody else's KIP. I think that there is a sort of opportunity for an Axe equals 1 sort of version of Diskless. I think it's going to have trade-off, like everything has trade-offs, but here it's going to have trade-offs for users. If there is a single leader like this, then it's still sort of on the user to set up sort of per zone topics, which is its own challenge and really is incompatible with keyed data. But they're seeing as like our design is sort of more of the Axe equals all implementation. I think it makes sense to discuss what the Axe equals 1 implementation looks like and discuss it on its merits. Like Ivan said, I don't think that they necessarily have to conflict. But it may be that like one of them is it doesn't make sense to support both.
Okay. I think so. I really think that your proposal should get in, no matter what. I hope we make it happen. There's like, but I guess we can talk about like why it's so good and why we think it's worth it. I want to dive now into the cost aspect, and another thing we haven't touched on is also the operational aspect. So, what costs does this KIP actually save?
yeah. So, well, maybe you, Greg, can go because you run the cost modeling and.
Yeah. So in the early exploration phases, the like first month of this project, it was extremely important for us to estimate sort of how much cost savings is here, just in order to understand like how big the benefit could be. So I ran a whole bunch of cost models that essentially take cloud pricing, published pricing. It simulates a cluster running with a certain instance size, a certain amount of attached disks, a certain amount of throughput, a certain number of brokers, and so on. All of the sort of relevant configuration parameters, and sort of simulates what the estimated cost is. And through those models, I found that the two most important aspects of the cost are that block size that I mentioned earlier, that is how big are the objects, how big are your requests, and inversely, how many requests you're making. And the other aspect is how long is your retention. So there's this effect where if you're using tiered storage and you're aggressively tiering such that the vast majority of your data is in tiered storage, and you have very long retention on the scale of a year or 10 years, you can get sort of reduced cost savings. Like there's less savings in Diskless because you're already saving lots of money through tiered storage. And the combined effect of these is that for very short-term data, like stuff that exists on the scale of an hour or 2 hours or 10 hours, you can get savings of like up to 90%. Like that's sort of where the thing asymptotically approaches. And that was like an extremely shocking number. We had to sort of confirm that for ourselves. And it really shows that like the vast majority, or this testing and modeling showed that the vast majority of the cost of a Kafka clusters today is in the interzone networking cost. And so that is incurred twice. That is when you produce to the cluster, if you're producing to a leader that isn't in your zone, you have to cross the zone and pay for that traffic. And then you're also incurring that cost on the replication. So when one broker is replicating data to another, that is also crossing a zone. So if you can eliminate,
and of course the same stuff on the consumer side.
Yeah, it's same thing on the consumer side, except that the consumers have had like the rack aware assignments for I don't know how long, a long time. So that one is less of a concern. But if you if you don't have that configured, then you run into the same problem where the consumer is also like making cross zone requests. So of course, like you don't just get rid of the networking cost, you add this new cost of the object storage and the request cost. And so there is a crossover point when you save like some amount of networking cost, and then you have more cost in this new request model. And that's where you're running like really small objects under 100 kilobytes. You can just blow your budget on requests.
Right. That's a great answer. So if I can summarize, then in traditional Kafka, whenever you write like 1 gigabyte of data to the topic, 2/3 of that goes to call zone just from the writing. So the producer is in another zone, the broker is in another. So let's say 600 megabytes, you're already paying the intra AZ cost in each cloud. And then because that's replicated, each gigabyte gets replicated 2 times, 3 brokers total. You pay 2 gigabytes of replication cost as well. And then every cloud provider charges you something different for that. So AWS charges you 2 cents, GCP charges you 1 cent, and Azure is actually free. That means also that like, the biggest savings you get in AWS, and then on GCP you still get pretty good savings, and in Azure the replication savings are almost non-existent. But also you mentioned a really good point with the disks. I spoke to another person recently about this, and I present the problem in the following way. Whenever you write like 1 gigabyte of data you ingest into Kafka, that needs to get saved in disks, right? And it's replicated. So in total, you're actually storing 3 gigabytes of data in the cluster for that initial 1 gigabyte. And cloud disks can be really expensive compared to S3. If you're using SSDs for your disk, you're probably paying like 8 cents a gigabyte in AWS. So you have like 3 gigabytes times 8. So you're paying 3 times that. But then, it's not only enough to pay for the gigabyte, because you have disks and you can run out of space. You have to actually model these disks to have enough ample space, enough free space so that you don't run out. So maybe you would have like 50% free space. And certainly, instead of paying, for 3 gigabytes, you're actually paying for 6, because you've provisioned 6 gigabytes in your disks. And that's how the cost tends to blow up with disks. And object storage is just so much cheaper than that. Let's run the numbers again. Like 6 gigabytes times 8 cents, it's what, 48 cents per gigabyte. S3 is just 2 cents. And S3 already handles the free space, and it already handles the replication. That's a massive cost difference, right?
Yeah, so we did model the cost of the disks. It's as close to a complete model as we can, and it is true that if you are not using tiered storage, the disk cost becomes outrageous. Like there is a scale at which it doesn't make sense, and that's part of why tiered storage has been so successful. Is that it is just strictly a cost saving measure, and it has very, very little downsides. I found that in the modeling, the disk space ended up being not exactly a rounding error, but was not a very significant source of cost, actually. So I don't have exact numbers in front of me, but to sort of give flavor, maybe like 60 to 70% of your cost was networking, maybe 25 to 30% of your cost was the actual instance hourly cost, and the disk cost and even in storage costs can be under like 5%. It really was not a substantial difference. Now, when you're
Is that with
looking
tiered
at
storage?
that's with low retention topics, and also with the active segments for very long retention tiered storage topics. So with tiered storage, like that's where I sort of want to differentiate Inkless, is that or Diskless, I mean, is it's really an optimization for the active segment and for replication, and not so much for the inactive segments, just because tiered storage like works so well already.
Right. Depending on how you configure it, right? Because some people may configure it to hold a lot of data.
Yes.
But yeah, makes sense. Yeah, I ran my own cost model. I even have a calculator online on a website. I'll plug it in here. But when I run the numbers here, I think like, if I put like a batch interval of, let's say, 300 milliseconds, the cutoff point, comparing just the diskless costs to the replication costs, because the diskless costs are kind of free, right? If you're not free, sorry, I mean fixed. They're fixed. If you're putting in S3 every 300 milliseconds, that means you get like roughly 3 and something puts every second. So your costs are kind of fixed regardless of how many megabytes you push, unless you hit the batch size limit. But running it here, I see like the break-even point for AWS is 400 kilobytes a second. So if you're using Diskless for a broker that has less than 400 kilobytes a second, that's going to be more expensive to use. The put costs are going to be higher. But the moment you go above that, the replication costs start to be higher than the S3 costs.
Yeah, I think, I mean, it's just like every piece of infrastructure it becomes more cost effective the more you use it, and it amortizes the sort of fixed costs. And I would say that like you still need to do smart sort of capacity planning with diskless topics. You don't want to have extremely underutilized machines. That's just going to increase your instance hourly costs. You don't want to have very over provisioned disks, because it's just wasting stuff. And I think that's sort of a big win for diskless also, and being able to decouple storage and compute, is the operational improvements. So because you don't have a lot of data on disks anymore, it's very easy to add and remove brokers. You can scale them up and scale them down. There still is data on disk for classic topics and such. But with some further future improvements, I think we can really get the operational stuff very well optimized and make it so that Kafka is cloud native again, or is now for the first time.
For the first time, yeah. Can you run me through a little bit of the operational savings? I can list a lot, but I want to hear it from you.
Yeah, of course. So
And how significant is that actually? Because we're only talking about costs, but a lot of people, when they talk about costs, they're not just engineers. We're engineers, so we want to look at what the AWS bill is, but mostly it's executives talking about both the infrastructure cost and the engineering hours cost. Like how many people have you assigned to manage this sort of cluster? So how do you think about that? The sort of like deflationary savings in engineering hours spent in managing issues in Kafka.
yeah, so of course there is it's difficult to like get a direct formula of how much each megabyte of throughput costs you in engineering time. So because, well, it depends on millions of factors, and but if we look like from long distance, we'll see that if your Kafka cluster is idle, it's easier to keep it stable than if it's like very loaded and has huge throughput through it. So, for example, like Kafka writes data to disks, and then disks becomes unevenly filled just because of random nature or like semi-random nature of the input data. So you have to eventually start rebalancing this the data between brokers. So keeping aside the cost of this rebalancing, because you also need to send this data over the availability zone borders. So it just consumes CPU, it just consumes memory, network connection, network bandwidth, and puts extra load on your brokers. So in Diskless, we shift this burden of balancing and, well, generally keeping your data around in a accessible state. Let's call it very abstractly. So you have a terabytes of data, and you need this data to be accessible by some like clients, like consumers. So, and keeping each gigabyte of this data on top of the existing volume is adding some complexity to your system. So, and when you start putting this in the remote storage, you're shifting a bunch of operational burden from your engineers to AWS engineers or like cloud provider engineers. So, and well, you're paying them money, but it's a decent money compared. So yeah, I know I'm being very abstract and very hand wavy because, well, as I said, there is no direct formula that can tell us, okay, like if we add 10 gigabytes of data to our cluster, it will increase by $5 operational
Right.
costs. Yeah, but this, like, my point being is that the dependency between those exists. So, like, we know that the more data we add, the more operation costs become. So that it might be non-linear, but still there is a link.
God, because like I've had cases where like I've rebalanced partitions in Kafka and it's taken days to do it. Granted that's without tiered storage, so you have to move a lot from the disks. If you use tiered storage, most is in S3, but you still have a fair amount local, and it's still taking me hours to have the process complete. So it sounds to me like if I was using Diskless, that would be maybe less than a minute because nothing actually moves under the hood. It's all in S3.
Yeah. So balancing is just non-existent in Diskless.
Right. So for Diskless topics, but we would live in a world where a broker would probably have both Diskless and classic topics. So how does that work then? So I guess like just rebalances become 80% faster, or have you also thought about like having brokers have roles? So maybe you would have like just a Diskless broker that serves just Diskless traffic.
Yeah. So Greg, maybe you want to.
That is basically like the first feature out of the MVP, like after the MVP is broker roles, because a lot of the operations on diskless topics benefit from locality. So if you are able to have producers that are producing to the same partition, like hit the same machine, that benefits all of the stuff downstream from that. If you're able to have the consumers and their cache on the broker side, like on a subset of the machines, then you have fewer network hops most of the time. There's lots and lots of cases where locality helps, and to your point, one of the places where locality helps is to keep all of the classic topics sort of segmented away from these sort of ideally stateless brokers that only handle diskless traffic. So in the future, I definitely see broker roles. I mean, it's one of our KIPs that we have to write soon. Broker roles where you can say, hey, this broker, it is for producer traffic. This broker is for consumer traffic. This broker is for merging. This broker is for classic topics. And in a world where those roles exist, you could have like Kubernetes or whatever else management plane auto scale each of those components as necessary, where it conforms exactly to your sort of assignment. So if you need more data in your classic topics, you can add a new node to the classic broker pool. If you need more consumer traffic, or you have a big batch job that spikes at one time of night, then you can just add a whole bunch of consumer brokers and not affect any of the producer brokers. I think that it's an extremely important feature, and a little bit of a miss that we don't have it, but we had to cut scope at some point. But it is definitely like a big ticket item for Diskless in the future.
Right. I mean, it's only been 7 months, so you can't expect the world.
Yeah. I can't get everything done at once. I'm sorry.
But then, like, if we're correct in what we've been saying, we just said earlier that like 80% of use cases fall under the Diskless umbrella. So, like, if we project this into the future, a Kafka cluster 3 years from now may actually look like 80% Diskless nodes and just 20% classic nodes.
Yeah, that's very, very, very possible. Especially if we like, once we have the broker roles feature, I think we may end up with extremely, extremely lopsided clusters where maybe there's like 3 brokers that are just enough to keep quorum over the consumer offsets topic, for example, and the controllers, and all of the brokers in a cluster are Inkless or Diskless. I think that's a very reasonable use case in the future.
That would be an amazing future. Yeah, I think I'm so excited about this. Like, the other operational benefits you get that we haven't touched on, is, well, first, not managing disks, not running out of disk space because S3 is bottomless, and secondly, not having to manage IOPS. Kafka deployer today has to be very cognizant of exactly what disks am I deploying, how much workload am I getting, is there a chance that the disk becomes a bottleneck? Any other things that you can think of that this new model helps rebalance this or faster? There's also now the ability, I actually looked at your code. So probably we can get into, how does the client choose a leader?
Yeah, that's a good question, because we spoke a lot about avoiding inter-AZ traffic, and now we are we discuss how it's done for replication by removing replication, but you cannot remove the network traffic between producers, consumers, and brokers. But what we can use is that now Diskless topics are leaderless, the Diskless partitions are leaderless, and that means that every broker could serve as a writing point and reading point for any client. If we add some pieces of metadata to this, that, for example, that clients communicate their, in Kafka this is called rack, but since we are speaking about cloud environments, it will be just availability zone in your cloud region. So brokers have racks, that is AZs, and clients have racks. So, and clients periodically ask metadata from the brokers, and we are free to, in the metadata for each partition there is a field called leader, right? Who is the leader, who will receive read and write for this client. So we are free to modify this metadata as we like, and we say, okay, we have this client is an AZ1, so we can check what we have in the pool of brokers in AZ1, pick one randomly, or currently we propose round robin because that seems just natural, and return this to this client. And this client, no modification needed. It will just receive as if it's the real leader in real classic topic. It will connect to this broker and start communication. So again, third-party clients will work, old clients will work, 2.0, whatever. They just need to support the basic metadata request protocol that every client supports.
Right.
And we can implement whatever policy we want. So we can assign, for example, one for each client, for each Diskless partitions, we can have one broker, or we can balance it in other way, like, for example, again, round robin through partitions. So there is no this policy could be chosen even by configuration.
Yeah, it can be dynamic too. You can be flexible. So that makes you become very flexible with rebalancing in general and handling not hot partitions, but like hotspots. And you're also reducing the amount of connections massively because back in the day, a client would connect to the leaders it wants to write to. Maybe that's 30 brokers and that's 30 connections. But now you're saying that one client may only use one broker, for example. So you just reduce the connections 30-fold.
Yeah. So, well, of course, you have to support these connections for classic topics. But and also that eventually we will rotate from one broker to another because, well, you have to reshuffle this stuff periodically so that you avoid specifically as a mechanism to alleviate the hotspotting. So, but yeah, if connections is a concern, you can reduce those because, well, we had these problems multiple times when we wanted to have huge fleet of producers, for example, and they want to connect to six brokers, then the number of connections flying around is not small. And of course, Linux has, well, any other operation system as well, has an overhead on network connections, so it has to keep buffers around and stuff like this. Right. So of course, maybe we are not speaking of huge savings, but, well, every penny counts.
So yeah, well, I'll keep on this theme of talking about the future a little bit. So if we have this, I'm again moving forward. So we have this feature. We have less connections on the margin, I guess. We can connect exactly where we put a particular client. Do you think that actually enables you to have better multi-tenancy in Kafka? So today we do not have multi-tenancy in Kafka. There are a lot of organizations that have implemented this and either offer it as a service or just have done it for their own sort of tenants. Like I actually won't try to recall. I think Uber did it, for example. And it almost this flexibility and choosing what producer client goes to what broker. And these brokers, assuming they're diskless, you're talking about a diskless world, assuming everything is diskless, you could, in theory, you don't even need 3 brokers to host a tenant. You can just use one broker, or I guess you do need 3 for the AZs. But basically, you get you get a lot more flexibility in saying, hey, I want Kafka to support multi-tenancy, and I can spin up just these brokers to host a subset of my tenants, and other tenants go elsewhere. And because I can spin up brokers instantly in and out, then I can really easily isolate a tenant, for example, if they're misbehaving or they're pushing too much. Or I can co-locate if nobody is doing anything. And it seems like you can create this system that's extremely flexible on both sides. Do you agree with that?
Yeah, I think that's a very good observation. I mean, in the same way that we're saying that it makes it easier to balance the cluster and make it homogeneous, it's just as easy to intentionally make it heterogeneous, make it so that you isolate clients from one another, you put groups of clients that have low traffic together, you amortize costs and stuff like that. It's all a matter of policy and not mechanism. And I think that it is really helpful to be able to do that on the scale of the metadata refresh time, which is 5 minutes, rather than hours or days in adding brokers, moving the actual topic ownership around, blah, 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 all of that sort of stuff. So yeah, I completely agree that multi-tenancy is a something that gets a lot easier to operate with diskless topics. And I think for that reason, we're very interested in the virtual clusters proposal in the open source. We think that there's a lot of sort of synergy, to use a silly word, between those different proposals, and I think they're gonna compose well, I think.
Yeah, I'm super excited about that, KIP, too. It seems like Kafka's community is just exploding in terms of contributions and everything. And it's a really exciting time. I guess one other thing for the future, I saw you had a roadmap actually in the Inkless repo. I don't assume that's an official roadmap, but just some ideas, I guess. And it mentioned Iceberg, and Oh, sorry, it did not mention Iceberg. It mentioned columnar formats, which I read that as Iceberg. I did a search and replace in my mind. My brain did that automatically. But columnar formats, I assume it means something like a Parquet. And you say Parquet, you want to say Iceberg immediately after because that's what's hyped up right now. I'm cognizant that Iceberg has not seen too much production usage yet, and in my experience and talking to people, it seems that people are mostly excited about it right now and talking about it. But we see a lot of movement in that space. And well, first, do you think that's going to come to Kafka? Secondly, does Diskless actually enable this in any sort of materially easier way or whatever? And in general, what did you mean by that roadmap item of columnar formats? I'm really curious.
Yeah, that's a very interesting topic, and we also listed this in the further work of the KIP. So we kind of bullish on this. So the idea being that we already got our hands very deeply into how we store data. So how we can shuffle batches, we move stuff around, how they are stored in different files on the remote storage. So it's already like on the table for us. We can introspect this and change stuff and do pretty much what we want. So, and having this capability in our hands, it's just kind of one more step forward, and we start storing data in something that is not Kafka native storage format. So Kafka, well, for the listeners, that Kafka native storage is not so it's kind of proprietary thing, can call it so. So it's not documented, it's some internal thing. Internally, it's just batches line one after another in segment files. Plus, well, the metadata is being file names and some piece of states that Kafka, partition leaders keep for them. So, but it's not something that, for example, any big data system could natively read. So it's kind of a holy grail in the streaming industry that we want Kafka we want to write data to Kafka, and then Kafka writes this data to some object storage. And then we want to take Flink or Spark and avoid Kafka altogether and point this big data system to the S3 directly. So read from these files without incurring any latency, without putting load on Kafka. So just like part of it. So it's not a fundamental enabler because you probably could do it other ways. But now, since we anyway doing lots of stuff with the data, so we could just make one more step. And also important distinction that currently we have, for example, Iceberg connector for Kafka Connect, which takes your data from Kafka topic and puts it on S3. So it's a solved problem. It's nothing new. The problem being is that in this case, you have dual storage. So you have Iceberg and you have your Kafka being whatever type of topic. So it's kind of, you pay twice. No, not twice, but you pay for two storages simultaneously. So the ultimate ambition is how to make the single storage thing. So that we store, for example, only in Iceberg. Well, we say Iceberg. Iceberg is a table format that supports multiple file formats, and Parquet is maybe one of the most popular, or the most popular, and others supported being Avro and Fork. So let's say we store in Iceberg plus Parquet on S3, and the big data systems read this natively. They have all the code for this already, and Kafka just do some transformations on the fly when consumers come. So this is probably solvable problem, and we need to find a way how to do this. But it needs careful designing and thinking about, because one problem is that Kafka, if we can call it so, but let's call it so, that Kafka is a row-oriented thing. So you store records by records, you read records as they go, and that's just one after another, just physically laid on the disk and or object storage. But Parquet is a column-oriented format, so you store columns in sections, one after another. So to read one record, you need to read multiple pieces of the file. So this becomes tricky, how to balance local buffering, so that you can reconstruct batches and records without spending gigabytes of memory just to buffer huge pieces of files. That's one problem. Another problem is that Kafka is schemaless. Well, Kafka is structure agnostic. Kafka stores just blobs of bytes. So of course there is a schema registry and various products similar to schema registry, but there is no enforcing of schema on the Kafka side. So there is a KIP, ancient KIP that has been abandoned since then, is that let's introduce broker side interceptors, and in these interceptors, one of possible interceptors would be the like broker side schema validation. So we always ensure that the data that gets to the broker is complacent to some schema that is known to this validator. So this is non-existent now in at least open source Kafka. I know that some proprietary implementation have their own broker side validation. So it's just kind of difference in original design and mentality between like original Kafka 10 years ago and some amazing future Kafka 5 years down the road where schemas and Parquet are supported. So when being in the middle between these 2 points, we need to find the route how to introduce all the missing pieces in the Kafka side and convince everyone that this will be beneficial for the community. So yeah, plus technical challenges that I mentioned, but that's probably would be easier than the people part.
Yeah, it's funny how we have consensus challenges, meaning social challenges, and the technical ones. I hope the schema thing is easier. Like I've asked people, and almost 100% have told me it's kind of crazy that Kafka doesn't support schemas. Of course, there are reasons, and you wouldn't make it, mandatory. Of course, it would hurt performance and etc. But yeah, that's super interesting, super interesting. And on the Iceberg side, on the columnar storage, you're right. I mean, the whole idea behind Iceberg and this open table format revolution was to not have so many copies of data, have it in one centralized place, only one copy, because you're talking about like many terabytes, petabytes actually in data lakes. So there it made sense. I think that's super cool. I have one more question on a future potential implementation. That's S3 Express, something that, again, some other proprietary implementation has. I mean, nowadays we have so many Kafkas, everyone has some sort of feature. Do you think Diskless is compatible with S3 Express? Do you think the batch coordinator is compatible with S3 Express, which is the idea of just having like a faster sort of S3 to lower the latency? And also, like, how much can it actually lower the latency? What do you think?
So with speaking on Inkless, which is our implementation and not Diskless, the open source form, Inkless right now does not have support for S3 Express one zone. Caveat being that you can do it, except you're limited to one zone durability. The sort of right way to do it is to write to 3 different zonal buckets and incur that sort of stuff. And so that strictly is not supported right now, but definitely is on the roadmap, I think, or on our radar at least. I see that there definitely is an opportunity to use S3 Express one zone in a diskless topic, because it sort of lets you cut away at some of that like lower floor that I was talking about earlier with the latency. If the time to commit the actual object becomes like a bottleneck that you can't sort of lower the buffering any further, then like switching to a faster underlying storage is definitely an option. And so I think there may be cases where there's like diskless topics and then there's diskless one zone topics, and And so there's like even more knobs to tune here. It definitely seems like an opportunity that we need to explore.
Interesting. So you are saying that we can have like both slow diskless and kind of faster diskless in that future.
Yeah, and maybe the faster diskless is like halfway between, for some definition of halfway, between diskless and classic topics. It all becomes a spectrum. And it reminds me of earlier in the conversation when we were talking about sort of new opportunities for higher latency stuff. Like maybe there's a slower diskless, like you actually intentionally go to like tens or hundreds of seconds latency. So I think that we're just sort of plotting one point on the latency spectrum where we had one before, now we have two. Maybe there's a third, maybe there's a fourth.
That's very interesting. That's very interesting. I think it's a great place to end it, at the intersection of batch and streaming, and we're gonna let the listener think about that more and more. Thank you so much for this long podcast. I really appreciate it. I think everyone is going to enjoy it a lot. Where can people follow you? If people want to ask you questions, can you give me some social media or somewhere where people can, talk to you?
Well, I'm on X and LinkedIn. We probably can post links in some like show notes.
Yeah, I'm on X, and if you care to email my Apache address, that would be funny.
Emails, of course, like.
But
sorry, yeah.
I would say that like you can just get involved with us on the mailing list. You don't need to necessarily talk to us specifically, but we're happy to answer your questions, and the community is happy to discuss things overall.
All right, awesome. Thank you so much, and I wish you a great day. This was great.
Thank you, Stan. It was a pleasure. Thanks for having us.
Thank you.